This is Physics 1020 and 1090. This is a lecture from Monday, March 16th. We're talking about Chapter 24, Wave Optics. This is the third video 3 from this lecture, and we're going to be talking about diffraction. We talked a little bit about diffraction when we were discussing Young's experiment. You might recall Young's experiment had two narrow slits, and they formed two beams of light which interfered with each other, and you got a bunch of what's called fringes, or white light and dark spots. However, we found that superimposed on those light and dark spots was a single slit diffraction pattern which modulated the amplitude of those light spots. So we're going to talk a little bit again about that single slit pattern that we discussed briefly during Young's experiment lecture, which was on Monday. Okay, so light comes in and hits an aperture. An aperture blocks the light except along one single slit right here. It lets the light through, and the light goes through and then hits a screen over here. Now, light will take off from any point within this opening and move, and they'll add up over here on the screen. So you get not just two rays, but many rays from each point in the opening, and they all add up, and they all can interfere with each other. And that total result is what's called diffraction, the diffraction pattern. So we aren't going to be able to calculate the diffraction pattern. It's rather mathematical for this class. I suggest taking an undergraduate optics class for that. However, I want to talk a little bit qualitatively about what that diffraction pattern looks like. Here, if you start with your light over on this side, and it passes through this single slit and then forms a pattern on the screen over here, and what you'll find is you get a large central maximum right at the center of the slit. Then it falls off to 0, and then you get these subsidiary maxima, which are much weaker. So you get on both sides a large central maximum and fringes along the edge that fall off with distance. And that is the classic single slit diffraction pattern. And then if you remember Young's experiment, we had superimposed on that a much more rapidly changing interference fringes from the two slit interference pattern. So single slit diffraction pattern gives you this kind of, the important thing is that if you're forming an image, you won't get an image of a point. You'll get an image, you'll get a blurred out image that's spread out like a diffraction pattern. So if you're taking an image, say this is a telescope, and you have a star out here that's a point source of light. When it passes through the aperture of the telescope, the opening at the end of the telescope, and then forms a image on the screen or the film or the detector, you won't see a single bright spot. You'll see a blurry spot from the diffraction pattern. Diffraction ultimately limits the resolution that you can have in telescopes, microscopes, in the eye, and any kind of optical device. Now, here's an interesting thing about diffraction. If you take light and you pass it through a very narrow slit, you'll get a very wide diffraction pattern. On the other hand, if you take light and you pass it through a very wide slit, you will get a more narrow diffraction pattern. So there's an inverse relationship between the slit width and the width of the diffraction pattern. If you want to get a very well-resolved narrow diffraction pattern, you want a very wide aperture. We've been talking about a slit. Now, if you look at the slit, we looked at it from cross-section, but if you looked at the slit end on, what we've been talking about so far is this, an opening in a otherwise opaque panel, an opaque screen. So you have an opaque screen. This hashing means it won't pass light, and you have a slit in it right here. You can have another type of situation where you have an opaque screen, but instead of having a one-dimensional slit, you just have a circular hole. So that's going to be what's shown over here on my right. Now, again, here's the circular hole. Here's the view if you have the front. If you're looking at the front of it, you see the circular hole. If you turn that and look at it edge on, what it looks like is it's blacked out except across the diameter of the hole, and that light gets through. So it looks from the side view very much like the single slit. And in fact, you get a result that's very much like the single slit in the fact that the light will come in, all the rays will meet on the screen, interfere with each other, and you get this diffraction pattern, which has a big, large central maximum and secondary fringes to the sides. It looks just like the picture I drew for the single slit. The functional detailed form is slightly different, but it's basically the same type of diffraction pattern. Suppose this circular opening is the end of your telescope, and you want to use the telescope to form an image of some stars. If the stars are well separated, the angular separation is very large between the stars, then as the light comes in, it'll form diffraction patterns on your detector or your screen. But if the angular separation is large, those two diffraction patterns will be well separated. They won't be overlapping at all. This one will have fallen off essentially to zero by the time this one begins to get large. So those are two distinguishable objects. In other words, if that was a telescope looking at two stars, you could easily tell there's two stars there. By the way, this material is coming in part from chapter 25, especially section 25.6. Doing it slightly out of order, but it seems to make more sense to me to talk about this in the chapter on diffraction. So, well-separated sources give you a distinguishable diffraction pattern. If you had two stars that were very close together, they're going to form two diffraction patterns on your screen. And those two diffraction patterns are going to be so close together that they're going to be overlapping. And what you're going to see is just a big blur. You're going to see a blur from one star and a blur from the other. And the two blurs are overlapped so much that all you see is a single blur. You can't tell there's two stars there. They're not distinguishable. So two stars shining on your telescope, you can't tell that they're separate stars because the diffraction pattern is so wide that it just blurs over. A scientist named Lord Rayleigh came up with a criterion to decide whether you could distinguish two stars in this way. He said that if you started with two diffraction patterns and the peak of this diffraction pattern is located at the first minimum of the other diffraction pattern or farther out, then you can distinguish the two. And so if the peak of this diffraction pattern is at the first minimum of this one, the two diffraction patterns are separate enough that you can tell that there's two objects there, and that's just barely resolvable. So that's the limit. That's how easily you can resolve two objects with a telescope. The limit is the angular separation. The minimum angular separation is 1.22, that's just a number that comes from the math, it's not very significant to us, has the wavelength in the numerator, lambda, and the diameter of the aperture, d, in the denominator. So again, a big diameter aperture, you're going to be able to get a smaller angular separation that you can resolve. If you want to make a really good telescope, you want to have a really big, large diameter aperture. That's called the Rayleigh criterion, and it tells you how you can determine whether you can resolve two objects. Now let me tell you a little history story about diffraction. Diffraction was originally studied by a scientist named Fresnel. Fresnel was a French scientist, and he developed a mathematical theory of diffraction. And he could apply this theory to a lot of various cases like single slits or circular holes. He also could apply this theory not to a hole, but to a circular object in the way of the light. So now all the light gets through except for one area where it's blocked. Think of taking a penny and sticking it in front of a light beam, and then you're going to look at what diffraction pattern gets created on the screen. So here's the situation. Here comes the light all across a large beam of light. Here is one area that blocks the light. That's that's like an aperture, but it's a obstruction. And over here is what you see in the detector. And way out on the side, you see all the light coming through and hits the detector. And also down here on this side, all the light hits the detector. Right at near the edge, what happens is you get some of these fringes that fall off with distance, and you get them on both sides. Very characteristic of diffraction. But there's also this funny little bright spot right here in the middle. Now, what happened was Fresnel came up with this theory. He was able to predict that there was going to be a bright spot at the center of this diffraction pattern. They had a big contest in France. This was in the early 1800s. Fresnel was a young man. He submitted his theory of diffraction to this contest because they wanted to find somebody who could describe the properties of diffraction. And one of the scientists who was older scientist who was on the panel to judge this contest by his name of Poisson. Poisson didn't like Fresnel, and he didn't like Fresnel's theory. So he looked at this prediction of Fresnel's, and he said, Fresnel's predicts there should be a bright spot at the center of this diffraction pattern when you block light with some sort of obstruction. That's obvious nonsense. And therefore, Fresnel's theory cannot be right. We're not going to award Fresnel any kind of award from this contest. He's not going to win this contest. His theory is obvious nonsense. But there was another scientist, Arago, who was also on the committee judging this contest. He thought to himself, well, not so fast. Why don't I go into the lab and do the experiment? So he set up a circular object, shined the light past it, and lo and behold, what he found was a central bright spot in the middle of the diffraction pattern. Nowadays, this is called Poisson's spot, even though it really shouldn't be called Poisson's spot because he didn't believe it was true. Fresnel predicted it, Arago saw it experimentally, and it's really an example of a scientific method. Oftentimes, the scientific method will work like this. You'll have a hypothesis, how diffraction works, and you'll develop a mathematical model to describe that based on that hypothesis. That model will make a prediction, then you'll go to the lab and test that prediction. That's exactly what happened in this case, and the prediction was verified and is shown to be true. Now, if you want to see a picture of Poisson's spot, go to chapter 24, figure 24.15. No, 24.17. 24.17 is this picture right here. It is the light, that the signal that's going to come through if you have a circular object blocking the light. And you might not be able to see it in this video, but you have your textbook. Get your textbook out. If you look at that, you have a large dark area where the light's blocked by your obstruction, but right at the very center there's a faint bright dot, and that is Poisson's spot. And that's what won Fresnel the prize and really established the diffraction theory. Thomas Young's experiment really showed light was a wave, but the diffraction theory really gave it some substance and a lot of detail. So that's all for this lecture. Next lecture, we will talk about diffraction gratings.